I'd like to welcome everybody to this webinar from the American Nuclear Society's Risk-Informed, Performance-Based Principles and Policy Committee. That's a mouthful. We use the acronym RP3C, and that's where you'll find it on the ANS website under standards. My name is Prasad Kadambi, and I am chair of RP3C. The purpose of RP3C is to help modernize ANS standards. Modernization has come to mean that risk-informed and performance-based methods are employed to overcome the difficulties that we all know about with purely deterministic and prescriptive methods. We've been calling these methods RIPB approaches. The Nuclear Energy Innovation and Modernization Act of 2019 explicitly recognizes the validity and the value of RIPB approaches. So we can now say that there is a statutory basis for using these methods and concepts and methods. There's a lot of guidance available on RIPB approaches, but most people have not had reason to become familiar with the guidance because the conventional approaches still dominate most things that we do, including standards development. Right now, ANS can be considered as a knowledge center for RIPB methods and concepts. The recordings of each of these sessions is available at the ANS website under RP3C. RP3C initiated these community of practice webinars on RIPB to enable practitioners of these approaches to share their knowledge and experience. We have scheduled these webinars for the last Friday of every month. And we welcome people coming forward and offering to make the presentations like what we will hear today from Brian Johnson of TerraPower, who will be talking about a new reactor called Natrium. Brian, please go ahead.
Thank you, Prasad. A quick introduction to myself. I'm Brian Johnson. I'm leading the risk and reliability team at TerraPower for the Natrium project. A lot of the PRA work is being done at GEH under their team with lots of help coming from Dennis Henneke and Jonathan Lee. So I thought I'd at least mention those guys by name before getting started here. I've been working on sodium-cooled fast reactors and risk-informed design since, before with my project at MIT. My thesis was on risk-informed design of SFRs, and I've been working at TerraPower since 2010, trying to add risk-informed methods to the way we approach our design and licensing at TerraPower. Today I'm presenting on SSC Classification. This is a presentation originally given to the NRC, and so this is how we are trying to engage with the regulator and how we are approaching our SSC classification. I'm going to go to the end really fast to show the acronym list. You can all take a quick look, maybe a screenshot. I'm not going to read through this because it'll take too long, but that'll help you if you get a little bit lost on acronyms. All right, the objective of this presentation is to give an overview of the Natrium reactor first, and then we'll talk about how we're going to use SSC classification under the LMP. And we have adapted a strategy to make the defense in depth adequacy that isn't exactly described in NEI 1804. We're meeting all the requirements we believe in NEI 1804 using a strategy that's, we think, a little more straightforward. This is a quick overview of some of the engagements that have happened and our overall schedule for the Natrium reactor. We've already submitted our regulatory engagement plan, and you can go look at the regulatory engagements we're having with the NRC. We've got quite a few pre-application interactions planned so that we can reduce our regulatory uncertainty. And we are following the Licensing Modernization Project, or NEI 1804, as endorsed by Reg Guide 1.233, as our primary methods of licensing the reactor. So we are trying to make a positive safety case using those methods. For some other interactions that you can go look at that we've had with the NRC, we've done the principal design criteria interaction, and I believe the decoupling strategy. Our testing plan and methodology, I think, is an upcoming interaction. And each of these build upon the risk insights from the prior ones. So including this presentation, that will help get you caught up to the interactions that we'll be having in the future. This is just a brief description of the Advanced Reactor Demonstration Project. This is an award that was won by TerraPower and the Natrium team, and we are in a congressionally mandated 7-year timeframe to deploy this technology. We're looking for improvements in safety, security, economics, and environmental impact. We're trying to use a simple, robust, reliable, and proven safety profile. And of course, we're trying to lower emissions by deploying a fleet of Natrium reactors that are compatible with a deeply renewable low carbon electrical grid. This is an overview of the Natrium design. Is my cursor visible?
Yes.
Okay, great. So in the orange box, we have the nuclear island, which contains the reactor building, fuel handling building, and the reactor auxiliary building. And that is connected via a pipe to the energy island that has an energy storage system as well as the turbine building. So the turbine can meet power demands as the salt tank levels are allowed to fluctuate, while the reactor operates generally at 100% thermal power whenever possible. They're decoupled via the salt piping and the reactor aux building, and that allows the nuclear safety to all be taken care of here while keeping the energy production equipment separate from the nuclear equipment. This is a cutaway of inside the plant of the nuclear island. We have the reactor building here that has the rack, which is the decay heat removal system. The reactor itself is an integral pool type reactor. The intermediate piping comes out here to the salt heat exchangers, and we have an intermediate air cooling system. This is a backup to the rack system. And as we go through this presentation, we'll eventually talk about how this hits the SSC classification and risk-informed methods. On the right side, we have the fuel handling building, as well as the spent fuel pool here. All right, so getting to the main meat of the presentation here is SSC classification. The purpose of SSC classification is to do this for each structure, system, and component according to their function. These classifications are used to determine the codes, quality standards that the structure, systems, and components will be designed, fabricated, erected, and tested to. The scope of SSC classification is all of the SSCs in the plant, and they must be categorized as safety related, non-safety related with special treatment, or non-safety related with no special treatment, which is shortened to NST. The safety classification for each SSC will be used to determine the level of quality assurance that's required and other special treatment requirements. The reason for the categorization will also matter in terms of making those special treatment requirements. I think it's really important to emphasize that it's the function that really drives the SSC classification. I'm going to give a short overview of the LMP process and how we are implementing it. We are going to be doing NEI 1804, we believe, without exception. We're not trying to take anything out of the process. We are adding a little bit to the process. The LMP includes licensing basis event selection, SSC classification, and defense in-depth evaluation that are part of an integrated process. There are direct connections then between the PRA, which is used to select the LDEs, the faulted events, and the deterministic safety analysis that is derived from the design basis events, which is a subsection of the licensing basis events, and quantifying the safety functions. The PRA is used to make the risk significance determination. This is presented to the integrated decision-making process panel, where the final judgment is made on SSC classifications, taking for consideration any missing scope or limitation in the PRA. So all of the risk-informed insights are given to this integrated decision-making process panel, which is a panel of experts to endorse or make the final recommendation for SSC classification. This diagram's been adapted from NEI 1804 figure 3-2 to clarify a little bit some design criteria input. So one thing that is made clear in NEI 1804 but not shown in their diagram is that as you start your reactor design process, you can't go straight to having a PRA. You have to make the reactor work first. And so a lot of the design criteria, especially those in Reg Guide 1.232, that's the advanced reactor design criteria, are very good guidance to start your design. And so when you do this first design, development, and analysis, you take your initial list of LDEs that comes more from historical practice, and you take these initial design criteria, again, using what has been developed through a lot of experience to do your first cycle on this before you perform your first risk assessment. And so design does precede risk assessment. And in that sense, we have to proceed to the design a little bit prior to risk-informed SSC classification being performed. Once we've got the PRA, then we select the licensing basis events as described in NEI 1804 based on frequency, 95th percentile, a lot more detail in NEI 1804. And then we evaluate those against the FC target. Anything we need to keep DBEs or high consequence BDBEs are required safety functions. And then we have to also evaluate design basis accidents, only taking credit for those safety related SSCs. This can actually be iterative if we find out that a DBE with only the SR functions from risk significance might make one of these potentially inadequate. And so you could end up with something that ends up being safety related that you've identified outside of the risk significance. Along the right side here, we have the risk significance determination process. And over here, we have the deterministic analysis derived from the design basis events that we use more traditional sort of chapter 15 type methods, but we've selected these events using the risk information. And then a defense in-depth adequacy evaluation and the integrated decision-making process panel input is used to make the final SSC classification with that integrated decision-making process panel endorsement. As mentioned, this IDPP is very important, and we have a slide later to talk about some of the specific things they consider. This is a more detailed layout of the SSC classification process, once again, from NEI 1804. This is figure 4-1. The preliminary SSC classification was performed using the results of previous SFR LMP tabletop analyses. And we supplemented this with engineering judgment on some of the changes that we would anticipate from the differences between Natrium and some previous SFR projects at GE and TerraPower that helped inform this. More detail and classification is going to occur as the PRA model improves, and we are going to have a list of LDEs that'll be selected, and this will be at a later NRC engagement that I think in the calendar you'll see is scheduled for the fall timeframe this year. So we get our input from the PRA and our LDE evaluation, and we identify the functions that are necessary in prevention of LDEs. And then we look at the SSCs that are capable of performing those functions and what defense in depth is necessary. This is then used to determine our required and safety significant functions. So the safety significant functions are either risk significant or defense in depth required. They could be both. So that's not a exclusive or. You look at a specific SSC, and if it is performing one of these required safety functions, then it is a safety-related SSC. If it is not performing a required safety function, then it is going to go into our, but it is a risk-significant function, it goes into the non-safety-related with special treatment. If it's not risk-significant, it may be required for defense in-depth adequacy. We think that this step is something we don't want to hit after the PRA, so we use a defense lines concept to try to meet our defense in-depth adequacy prior to the completion of the PRA and looking through this process. If so, then it's classified as NSRST in order to assure sufficient defense in-depth adequacy. If it's not required for either, then it goes into the non-safety related with no special treatment. Very importantly, and I'm going to go back a few slides, we expect to use these methods to classify all items in the energy island as non-safety related with no special treatment. The current work we're completing that we're going to do to support the PSAR is revising our SSC classifications using the PRA. This allows us to select our licensing basis events and perform the analysis to support our DBA selection. That is done by taking the DBEs and using only those required safety functions in SRSSCs. We're also finalizing the defense line concept across the different safety functions. There's the fundamental safety functions that we'll talk about here briefly. And then we're also going to determine all the special treatment requirements that we're going to have to assure adequate performance of SRSSCs and also NSRST, the non-safety related with special treatment SSCs. And then for the FSAR, we expect to confirm the adequacy and update any LMP analysis if any significant changes are identified for the as-built Natrium reactor, which is being licensed using the Part 50 process. So I just mentioned the different sorts of safety functions and how SSCs are classified according to function. When you use the LMP, you've got a variety of safety functions. You have the fundamental safety functions, control, which is reactivity control, cool, which is removing heat from the reactor fuel. That could be fission heat or decay heat, and contain. We want to keep the fission products within a sealed envelope and away from the public. The PRA safety functions are any function that we include within the PRA that may contribute to the prevention or mitigation of the release of radioactive material. Required safety functions we've talked about a little bit, and those are those functions that are credited in design basis events or high consequence BDBEs to meet the frequency consequence target curve, or in those design basis accidents we derive from the DBEs, and those have to meet the 10 CFR 5034 release limits. That's a 25 rem 2-hour dose limit. Risk significant safety functions are any PRA safety function that keeps any LBE, that includes AOOs and BDBEs that do not initially have high consequences within the FC target, or if there is a significant risk contribution to any of the quantitative health objectives. That's an integrated risk metric. Safety significant functions are any PRA safety function that's needed for defense in depth adequacy or is risk significant. This can be confusing, so here's a Venn diagram, also from NEI 1804, figure 4-2, the definition of risk significant and safety significant SSCs. So we have all the SSCs. Anything within the PRA can be performing a PRA safety function. The safety significant ones are there for defense in depth adequacy or risk significance. And then the safety related SSCs, as we mentioned, are those that are necessary for those select set of events, or potentially, as I mentioned, DBAs that might not be risk significant, but end up being safety significant. So we talked a little bit about the defense in depth adequacy, and the design application we're using for defense in depth is a defense lines approach. This is consistent with IAEA SSR 2/1 defense line definitions. It varies slightly from that, and we make it consistent with the requirements of NEI 1804. So first we identify mitigating functions for any given LBE. We assign functions to the defense lines. So if we have a function in the PRA that's something like a reactor controller, reducing power using normal motor control of the reactor drives, then we say, well, let's assign that to defense line 2, since it's the first way we respond to an event. We ensure that there's 2 functional defense lines capable of mitigating every AOO, and most DBEs, it is allowable that a DBE could be mitigated in just defense line 3 if it's robust enough. Application of independence and diversity requirements is also there for those defense lines, and that helps support the adequate defense in depth. What's really good for this is it supports a very early indication of our safety classifications prior to the PRA being completed. We know that the defense line 3 functions will match with the safety related assignments in the LMP. The defense line 4 functions will generally align with the NSRST assignment in the LMP, but there could be some that are NST. And in some cases, defense line 2 may be NSRST if it's risk significant in the AOO region, or because it's expected to be used in an event where DL3 might fail, but the defense line 2 function was not compromised. This approach is intended to minimize the number of needed design iterations towards the end by basically setting a requirement up front for defense in depth adequacy for the postulated LBEs, so that when we get to the end and look at the various LBEs and the available functions, we can meet the defense in depth adequacy requirements. So here are the layers of defense, and I've been calling them in brief the defense in depth adequacy requirements from NEI 1804, and there's more in that document. And what we're focused on right now is the plant capability defense in depth. So when you evaluate your defense in depth, this is part of your risk-informed process. Aside from checking against the frequency consequence curve, we also have these quantitative and qualitative guides so that for each layer, we can go through and show that we have some functions available. So if we start out with something like uncontrolled rod withdrawal as an example event and how we would go through this, we would say, well, normally we have our normal control system, and then we have in layer 2 detection and control of that abnormal operation using the plant control system and set points that will cause the automatic reduction of power to prevent the DBE from occurring, and will return to normal. If that were to continue to happen and we couldn't compensate appropriately, then we have things like reactor scram to terminate the operation of the plant, and then we would transition to a decay heat removal scenario. If for any reason that might not work, then we have perhaps another method to get reactivity insertion in. In the case of natrium, we have inherent reactivity feedback characteristics that help prevent that accident from progressing to a fuel failure condition. And if we can limit those accident releases, then we can prevent any need to have an emergency plan for that particular event. That said, we do have to consider the full PRA for all events, make sure we have sort of sufficient defense in depth along all these lines. Some of the important things in this table are that we have no single design or operational feature, no matter how robust, is relied upon to satisfy all 5 layers, and that we want to meet the FC target. One thing that was noted as we went through NEI 1804 is the guidance per layer here on maintaining DBEs frequency below 10-2, BDBEs below 10-4. This is referring more to the FC target and making sure that those BDBEs with a consequence that would exceed the DBE allowables is kept below that range. And likewise, for the DBEs being kept out of the AOO range. Since events are defined based on their frequency and not on their consequence in NEI 1804, by definition, all DBEs already have a frequency less than 10-2 per plant year. And if it goes above, it just becomes an AOO and your allowable changes. So how does this defense line concept work in practice? We have a postulated initiating event, and these postulated initiating events are separated by their frequency. So for AOO PIEs, we expect to have most often a defense line 2 function that will prevent the AOO from progressing, and we'll have a safety related function, and that would provide sufficient adequacy. We may also use a safety related defense line function as well as a defense line 4 function. Which note 2 is important here, and I mentioned it before. Defense line 2 functions can also be credited after defense line 3 functions if they are not affected by the assumed failure. For design basis event, postulated initiating events, we have the same general requirement with a few exceptions. For spurious CCF postulated events, this is, again, prior to completing the PRA, we will reassign these also per LDE. Then we require a safety related function that can manage any postulated common cause of defense line 2 or 4. And then for some defense line 3 functions, if we had some common cause failure of all of our safety related systems, that's things like failure to scram, so an at-risk type event, then we would expect to have a way to mitigate that prior to using a barrier type defense line 4 function that would help prevent the release. This is a quick example of the defense line concept. Defense line 1 is related to programs and features of the design rather than functions. So this is going to be things like your inspection program, things like keeping your sodium processing system inlet above your IHX inlet, such that any postulated leak out of the sodium processing system cannot cause a loss of coolant. These design features are very important, and we capture those through this concept where they're sometimes difficult to actually see in the PRA because in the PRA, they become screened out as not causing an initiating event. Defense line 2 is a normal response to most postulated initiating events. So for natrium, this is heat removal via the IAC in active mode using the cool fundamental safety function once again. So that active mode operation is classified as no special treatment, non-safety related with no special treatment. Defense line 3 is typically sufficient for all of our DBAs and DBEs. So we have, in this case, heat removal via the rack. Within the actual definition of these LBEs, we expect to have some LBEs that are going to be design basis events where IAC active modes available. And so when that's recorded in the PSAR, the DBE version of the event will take credit for everything, including this IAC and active mode. And then there will be a derived DBA that only uses the rack in SR mode. Passive mode IAC is used as the fourth defense line. And this is mainly done for defense in depth for our cooling function. Rack is a very robust system, expected to be very reliable. And so having this alternative means of removing decay heat is not necessary to meet the frequency consequence curve, but provides additional assurance that we have two ways to perform that function. Going back to no operational feature, no matter how robust, is meant to make all these layers or to be to all the DBEs. So we also require it here. So these are the sort of defense in depth measures that we expect to be able to get with the defense lines concept. And then finally, defense line 5 is related to emergency planning and will eventually be developed, but isn't directly related to cooling the reactor core. We believe this lets us, significantly simplify our safety-related cooling based on the features of the plant. We essentially have just the natural circulation air system, which has no ASME welds, is operated at atmospheric pressure, and has an unlimited supply of air. It's fully passive and always on. It's sort of this singular rugged system. But we maintain defense in depth, as I mentioned, with the IAC. Previously, we mentioned the IDPP. The Integrated Decision-Making Process Panel reviews the risk information that's provided to ensure that the scope of the PRA is sufficiently complete to make these SSC classifications. They ensure that LBEs and SSC have been identified and adequately described, that the basis of the required safety function selection is sound, that the safety-related SSCs that have been selected can perform the RSS for all the associated LBEs, that protective measures for any risk-significant LBEs are well understood, that any specific protective measures against common cause failure are identified. You want to have not just the CCF notionally, but that common cause failure usually has some postulated cause. And so you can have protective measures and you can have a cause and effect model for your CCF to make sure you are trying to mitigate CCF where it's been identified. And that any available risk benefits characterized, so that there are sensitivity studies that have been performed and trying to determine if there's any more margin that can be easily achieved through any either simple changes in classification or inspection frequency or things like this. I thought we had one slide with the FC curve on it, but I don't have it. So unfortunately, I don't get to actually show how the risk determination process is made. I was only able to describe that verbally, but we can now open it up to questions.
Okay, thank you very much, Brian. We do have one question in the chat window. It says, how does the PRA and design groups plan to handle, let's see, one second. Plan to handle revised PRAs, changing SSC classifications. Is the organization open to reclassifications in the future, or does the organization have a plan to completely avoid reclassifications during the design process?
That's a good question. So our initial classification, we used a set of PRA safety functions that we thought was sufficient. And then we stacked on a little bit of conservatism and added one or two additional functions. and said, as the PRA details change, we might be able to classify our SSCs down. Generally speaking, we try to slightly overclassify, and then as we get detail, the classification could move down. In a few cases, it's possible that we'll start with a classification and potentially find out based on a PRA update that we've gotten it wrong, and it becomes a required safety function later on. And we do track those risks in a sort of a risk register along with the SSC classification itself. And so some features, particularly like sodium processing system isolation, cover gas isolation, these are the sorts of functions we think might move up or down for the Natrium design. And we will accommodate any changes through those design phases.
Okay, thank you, Brian. Next question is, are support systems for DL2 and DL4 independent from those for DL3?
Yes, they are. So for the defense line concept, it's important that the support systems for defense line 3 be independent as much as possible. And in the case of Natrium, I don't think have any where they are shared at this time, that you have independence of the support function. So, reactor auxiliary cooling system is completely independent from the IAC. Between 2 and 4, though, they're sharing that IAC piping. They have the same sodium, containing components, and they're using the same air dump heat exchangers. But we don't need the electrical system or the fans that use in the active mode to be available in the passive mode.
Okay, next question. You didn't give much attention to scenarios initiated by a major external hazard, like a huge earthquake. Their special feature is that the load they bring can affect many, sometimes all SSCs, all at once. How does your SSC classification scheme cope with the challenge brought by these large hazards?
That's a great question. And within NEI 1804, the recommended method is to use design basis external hazard levels. And we would define those on a risk-informed basis, where we're going to target frequency a little bit below the DBE range to give a little bit of margin to that performance, and ensure that all the safety-related SSCs are capable of functioning for that design basis external hazard level, and not necessarily generating additional LBEs. It is possible that the specific very large external events could have consequences or failures that are outside the FC target. The FC target is not a hard acceptance criteria. And so that residual hazard that's historically been accepted for other reactor designs in the 10-6 to 10-7 region is a discussion that we'll have to have with the regulator.
Okay.
Brian, this is Bob Budnitz. Can I ask a follow-up question to that one, the one I just asked?
Absolutely.
Yeah, I mean, it's simple enough. I'm very familiar with 1804 and LMP, and what you just said is completely right. That is, there's a design basis earthquake, which is site-specific, and it all has to meet what you just said. But we know that if the design is executed properly, no SSC that matters is going to fail during the design basis earthquake. It takes a bigger earthquake than that to cause seismic failures.
That's correct.
If it's properly designed. And that bigger earthquake then sort of goes outside the scheme of relying on what the LMP requires you to do, that you just said for the design basis earthquakes. I don't know if you see see the dilemma. You've got to find a way to identify which ones fail at which large earthquakes and how big they are and how frequent they are and what combinations come together. And that is sort of outside, not sort of, definitely outside the scheme of relying on the design basis earthquakes to figure everything out for classification.
I understand what you're saying. I think that within this system, if I've already identified those components I need that are safety related and getting that special seismic treatment, finding the specific fragility needs or special treatment we want to do for those will include looking at the seismic risk, will involve the integrated decision-making process panel to see what can realistically be done to mitigate that seismic risk. And you're still going to identify the same systems. Ultimately, if we consider the Natrium design, the goal is, of course, to keep the reactor vessel intact, the rack functioning, and the rods inserting. And if you eventually postulate a seismic event that is big enough to fail all of those, which will happen at some number, say 10 minus 7, maybe a higher number, we include that in the risk information. And that doesn't change the classification, though, of these systems. They're still the safety-related systems. So that's my answer on that one.
Okay, by the way, what you just said, you didn't say these words, but the idea that you just said is right. That is, the identification you got to do. But then the special treatment is to identify which of those SSCs you need to make stronger. I use the word stronger vis-a-vis the earthquake load in order to assure that the sequence doesn't develop. So it comes down to identifying the special treatment after you've identified which SSCs you're dealing with.
That's correct.
Yeah, thank you. So we're on the same page. Thank you.
Okay, next question. Is there a potential path for screening out fire, high winds, and internal flooding? Or will these be modeled to determine additional SSC classifications and contribute to DID, defense in depth?
For Natrium, we are performing PRA scoping for fire, high winds, and internal flooding. The result of those scoping analyses has not driven us to identify any additional systems or additional LBEs that we would need to accommodate. If we applied those same principles and some of the assumptions changed, or if we had a different design, that might not be true. We do things to prevent, flooding sources from being available. We don't want to flood the rack. And we also don't want water generally to come into contact with our sodium containing components. And so there's a lot of alkali metal fire protection requirements that help prevent internal flooding for us. But if we had an internal flooding risk and it was in the DBE region, we might find there are SSCs that we need to somehow mitigate that flood. In the case of Natrium, we don't believe that's the case.
All right, thank you.
Let's see, at this point, you have responded, Brian, to all the questions posed in the chat function.
I think there's one more from Franklin Hope. It says, are we considering proposing expanding the scope of what treatments are allowed by 10 CFR 5069 to provide more cost savings? My answer to that is NEI 1804 is not directly an implementation of 50.69. It's a different SSC classification process. And it will be, I suppose, one of the first, or other advanced reactors are also using NEI 1804. We're going to pick special treatments that we think ensure the safety function as identified. So in cases where we have a risk significant safety function, we'll set things like risk targets, and we'll use risk-informed ISI. For defense and depth adequacy, we'll set functional performance requirements, but we might not have a strict reliability requirement since there's not a large impact in the PRA for the sake of the argument.
Okay, thank you for picking up that question, which I missed. Let's see, did I miss anything else? But if at this point, somebody has a question, you're welcome to unmute yourself and pose the question. Okay, I don't see that there are any further questions, and I think what you provided was a very comprehensive sort of guidance as applied by 1804 for the Natrium reactor. And I would just point out that some of these concepts do involve a performance-based approach also, although the performance-based aspect was not explicitly identified. Let's see, there is a new question just came in. Oh, it says interesting presentation, thank you. But at this point, I do want to thank you, Brian, for making the time to share your knowledge and experience with this risk-informed and performance-based approach applied to this new reactor. And I wish you all the best with success in this project. And if you have any other questions, you're welcome to send us separately an email, and we'll try to communicate with Brian and get you answers to that. So at this point, Pat, I think we are done with the April Community of Practice session. I want to thank everybody for attending this, and hope you will suggest future sessions for RP3C to host. So thank you all. Pat, I think we can sign off.
Yes, thank you very much.
Thank you.
Thanks.